Today we're going to have four big theorems that we're going to look at. And they're all going to relate proportional parts within these triangles. The first, we're going to look at this theorem, and it's actually converse. The triangle proportionality theorem says the following. If a segment is parallel to one side of a triangle and it intersects the other two sides. So we're going to start with this setup. So we have a segment that's parallel to one side of a triangle and it intersects the other two sides. Okay? I'll draw a picture of this in just a second. In fact, I'll actually throw it up. So we have kind of this picture. We have a triangle. And we have a segment that's parallel to one side and intersects the other two. Okay. And I'll even label this thing to give us a frame of reference. A mid-segment could be an example of this. It's not necessary. So a mid-segment is actually a special case of this theorem. It doesn't necessarily have to be the mid-segment. It could be anywhere in here. But it could be a mid-segment. This theorem says that our theorem is going to claim something about the created sides, the parts that we're going to draw. And in fact, it's going to say the following. For this setup, then the parts of the intersected sides are proportional. So it's saying then the parts that we've created by intersecting those two sides, those things are forced to be proportional. For a mid-segment, which is parallel to the opposite side, we saw that the proportion is actually 1 to 1. The sides are equal. The two parts are equal because they intersect at a midpoint. For if it's not the mid-segment, then they're not necessarily the same. In fact, they won't be the same, but they will be proportional. So for example, in our little drawing here, if I know this setup, then I can claim the following proportions. I could say that AD to DB has got to be the same proportion as CE to EB. These two sides and these two parts are proportional, is what this theorem says. The converse of this is also true. If we go in the reverse direction, so if a line intersects two sides of a triangle, such that the parts are proportional. So if all I know is that I have a line that's intersected two sides of a triangle and those parts it makes are proportional, then I can actually claim the reverse. I can claim that the line is parallel to the opposite side. Parallel. Third side. Is a claim we can make. We do the reverse of it. So if you have that same drawing, but if I don't tell you it's parallel, but I do know the lengths of the sides, If those parts are all proportional, then I know something that's forced to be true is that that line that intersects the sides is parallel to that third side. So, for example, if instead of knowing that these are parallel, if instead of knowing they're parallel, instead I know something about these sides. If I said, how about we have like 6, 2, and like 12 and 4. Yeah. If like I know those side lengths, if these are proportional, then I can claim something about this line that I drew in. So if I can say like 6 to 2 is the same as 12 to 4. Are these sides proportional? These are equal ratios. So yes. Those are equal ratios. So therefore, something we can claim is that DE is parallel to AC. So our claim is then we know that those things are parallel. Would be the claim. Since they're proportional, then we know if we have some parallel sides. So a couple of quick examples. If I want to find the length of, say, AB, I don't know what this is, but I do know I have a triangle, and I have a line that's parallel to one side, and it intersects the other two. So I know that it's dividing these segments into proportional parts. So like a proportion I could set up, I could say like x to 5 is 12 to 6. It could be one proportion. An equally valid proportion could be x to 12 is 5 to 6. Is an equally valid proportion. X to 12 is 5 to 6. You could say 6 to 5 is 12 to x. You could say 5 to x is 6 to 12. In any case, you end up with 6x equals 60. X is 10. You could use scale factor if you wanted. You could say that to go from 12 to 6, I would multiply, or maybe a better way to go, if I want to go from 6 to 12, I double it. So when I go from 5 to x, I should double 5. You get 10 as well. Would be another way to look at the problem. But they're proportional. That same game, if I ask you, is BD parallel to AE, then we can check to see if we create proportional sides. And if we do, then we're good to go. So like, I can say is like 3 to 6. We'll ask the question, is 3 to 6 the same as 4 to 8? Is that a true proportion? Yeah, you could check that. Say 24 is equal to 24. So yes. So BD is parallel to AE. You can play the same game. You can say like 2 to 1, 3 to 1.2. Are those equal ratios? One way you could check that, you could just cross multiply and see if you get equal things. 3 is equal to 3 is not equal to 2.4. So then B is not parallel to A. Would be a claim. I could ask you, like, your homework question may fill in like an x here and say what value of x makes the line parallel to the third side. Find what x makes it proportional. So. On the reverse side, our third theorem for today, the parallel proportionality theorem, is an extension of the first one. So rather than only having one triangle and two parallel lines, well, if we now generalize and add maybe a third, and you can use this to generalize farther. But it says the following: if three parallel lines are intersected by two distinct transversals. Distinct meaning different. Just two different transversals. So our setup is the following. We have now, instead of just two parallel lines, now we're going to give you three parallel lines. And you can use this to generalize even further if you want to add more than just three. But we have three parallel lines and we intersect them with two different transversals. So like an example of that, like a drawing might look like, say I have 1, 2, 3 parallel lines, and I'm going to intersect them with two different transversals. Those are all parallel. There's one transversal. How about there's a second transversal? So our general setup looks like this. I have three parallel lines, then I have two transversals drawn in however I want them. They're just transversals. They may intersect very near, they could intersect far away. They may never intersect. But the two transversals are going to do the following. My two transversals are going to create segments that are proportional to each other. It's going to do the following. So if I have this setup, then the segments created are proportional to each other. Not necessarily equal, but they are certainly proportional. The reasoning is just an extension of that of the previous theorem. If they intersect, then I can make similar triangles. If I have similar triangles, then all the parts are proportional via our previous theorem. So if I just do it a bunch of times, then so if I want to find, say, some given lengths, I have three parallel lines intersected by two transversals. The theorem, our previous theorem, says that these parts, that the segments created, are proportional to each other. Or I could say DE over EF. DE to EF is got to be the same ratio as AB to BC. Or by plugging in the values, I could find x. I could say like 6 over 8 is x over 10. X is forced to be, what, 7.5? In our second example here, the lines aren't marked as parallel. So before we even bother to apply this theorem up here, we better make sure and reason with ourselves that we actually have some parallel lines here. Isabel? Yeah, if you have corresponding angles are congruent, then we know the lines are parallel. That was back in chapter 3. So since corresponding angles congruent, that forces these lines to be parallel to each other. And knowing that, now we can apply our previous theorem. So now we could make some proportions based on the segments here. So I could say maybe like x is to 9. as 3 is to 3.5. Or x is to 3 as 9 is to 3.5. Or one of the other various combinations. 3.5x is equal to 27. Which you end up getting a repeating decimal, if I'm not mistaken. Rounding this to the nearest, say, hundredth, what do we get? Does anyone have a calculator that did this? If we start with decimals, you're welcome to end with a decimal. Our last theorem for today, our last proportionality idea, involves an angle bisector. It says the following: if about an angle bisector of a triangle intersects the opposite side in the following manner, such that the parts created of our third side are proportional to the two sides of the original triangle. So a good picture of this would be like example 4, part A. We have, here I have a triangle with an angle bisector drawn. Notice that I know it's an angle bisector because segment XW breaks angle XYZ into two equal parts. This is forced to be an angle bisector. According to this theorem, the two segments that are created of this side of the triangle are proportional to the two original other sides. So like WY is to WZ. WY is to WZ as XY is to XZ, namely. Two parts are proportional to the two sides if you have an angle bisector creating. Or to find A, our missing variable here, we could say 3 is to 4 as A is to 6. Could be something you can claim. Cross multiplying, you should get A is 9/2 or 4.5. How do we go about finding x in our second triangle here?
You gotta find out what the limit proportional to x is, but because we don't know what x is, we have to use that thing that we learned in the book 6.2. So it would be 20 minus x over x.
This was like the key idea, is that I know this whole thing's 20, this piece is x, so then all we need to do that's missing really is the expression for this piece. And if we understand that it's just the whole thing minus x, or 20 minus x, then it's just a matter of applying the previous theorem. So yeah, so 20 minus x, we can say 20 minus x over x should be equal to what ratio? 11 over 14. And from there you could cross multiply and solve. You should get, see, we end up with the following. You end up with 14 times 20 minus x equals 11x. 280 minus 14x equals 11x. By distributing, 280 equals 25 x's. Therefore, x is equal to, what's x equal to? To 11.2. Right, we add 14 to both sides. 11 plus 14 is 25. Is it 11.2? I'm going on faith here that someone else did it. But again, the key idea for this guy is you need to come up with an expression for what this piece is, and then it's a proportion. Cross multiply and solve.